All right, there we go. So we'll start chapter 2 now for Gilbert Community College Geology. As stated before, if you have any questions, feel free to raise your hand or comment them in chat or whatever you need to do, really. So we're going to talk about plate tectonics. In order to have an understanding of geology, you know the engine behind geology, essentially the how of geology. Plate tectonics is that how. Plate tectonics is the motion of the earth that causes every other thing in this class to actually function. So, talked last time about the different layers of the earth from chapter 1. The earth's rigid outer layer, the lithosphere, is in fact divided into several plates. These plates, the plate part of plate tectonics, move slowly across the surface of the earth, whether they are the surface of the earth and they move slowly. These plates contain both continental and oceanic crust or lithosphere. So when I say crust, I mean both continents and ocean. And lithosphere is the sciencey way of saying that it is an argument. Here's an image of these plates that I'm talking about. In reality, the plates are subdivided a lot smaller than this. This is a real blown out view. North America, for example, has lots of individual subplates within it. But this is the idea. And each of these plates moves, essentially floats, if you will, sort of, like something that floats, whatever you want to choose. And they bump into each other and they move around. We'll discuss how they interact with each other more and how they create the world that we live on. Theory of plate tectonics. Well, let's start with the asthenosphere. The asthenosphere is the layer that is directly below the lithosphere, or the crust, the outer ridge of the Earth. It is harder and weaker than the above lithosphere, the rigid layer, and allows for motion of the lithosphere. So in essence, you can consider the asthenosphere to be this malleable plastic-like substance. Still a solid, but sort of like maybe like a molasses caramel type structure, wherein there is movement and flow within it. And then, as you imagine, if you have something floating, the current below what it's floating on will carry it, right? You're floating in a lake. The current, you're going to flow along with the current of the lake. That's essentially what's happening here. Since the lithosphere, since these crusts are floating, moving around, they're not all floating always in the same direction. So if different chunks of the lithosphere, different plates interact with each other, you have what's called a plate boundary. A plate boundary is, well, the boundary of the plate, right? All major interactions among plates occur at their boundaries. You can have interplate interactions and stuff like that, but for this class, we're going to mainly focus on plate boundary interactions. So that's a super basic intro. Let's talk about continental drift and what that theory was. Alfred Wegener in 1912 proposed his theory of continental drift, right? In the origin of continents and oceans. And what his idea was at one point, before the Earth was as it is now, it was different. It was all the continents of the Earth, Africa, Europe, Asia, North America, South America, Antarctica, all of these continents were in fact clumped together into a supercontinent, which he called Pangea. Over time, Pangea broke and the continents drifted away from each other into their current settled positions. Image shown here, we can see the model reconstruction of Pangea at the top and Wegener's diagram of what he thought it looked like down below. Notice he wasn't exactly right, but still pretty close, right? North and South America, Africa, Antarctica, these are all more or less where he thought they would be. Cool. So why did he think this way? As we talked about in chapter 1, the prevailing theory of geology, it wasn't even really geology back then, the prevailing theory was catastrophism, or essentially the biblical Noah approach to geology. Why do mountains exist here? Well, the flood happened and mountains arose there for reasons. That was the prevailing theory. Wegener thought things differently. Wegener looked at 4 key points. He looked at the jigsaw puzzle fit of continents, the fossil occurrences that match across oceans, rock types and structure matches, and evidence of ancient climates to support his theory that all the continents are once connected into Pangaea and then later expanded out. Wegener had all these arguments for his theory of Pangaea. One thing he lacked, however, you're going to notice, is a reason why the continents float. Because, right, you can jump on the land, it doesn't feel like you're floating on something. This was an issue for him. So, what were these evidences that Wegener saw? First one, I said, the fit of continents. It's very interesting the way that you can take the continents specifically around the Atlantic Ocean, and if you close the Atlantic Ocean, the continents surrounding it come together very well. In this picture here, Africa and South America fit together a bit too well, right? The eastern tip of South Africa fits very nicely into the western part. South America fits very nicely in the western part of Africa. Why is this? Maybe because they once did fit together, Wegener thought. He also noticed, as shown here, that certain rock structures and certain geology seem to exist both on the eastern side of South America and the western side of Africa. Why would that be? Why would 2 continents separated by an ocean share certain geology? Not only do they share geology, a lot of them also shared fossils. Well, that's kind of weird, right? We have something like this Lystrosaurus up top, that goofy-looking guy with the tusks. His fossils appeared in many different parts of the world. But he didn't necessarily cross the ocean, did he? How could his fossil appear in these sections of the world, but not other places? So he wasn't uniform. He wasn't all over the world. He was only in these parts, and these parts he happened to exist in places that look like they would connect otherwise. Maybe that's evidence of something, right? The mesosaurs, shown there on the left, existed on the western side of Africa and the eastern side of South America. In the same rock layer that was also shared. Maybe that means something. A humorous cartoon from around Wegener's time, maybe a little later, showing possible ideas of why these fossils existed all over the place. All these are in fact true. All these are considered ways that, as it says, critters get across the ocean. However, you need evidence of these things to exist. If you don't have azimuthal links, such as the link between Alaska and Russia, you can't use that as a connection point for animals to cross, right? Humans got into the Americas via an azimuthal link. Island stepping stones. Some creatures possibly got to Australia via the island stepping stone method, is thought, or Japan. Rafting exists, but only for small creatures. We see this happen nowadays. Therefore, continental drift would be the best argued approach as to why you'd have the same animal on both sides. And look here, these sad dinosaurs get their heart broken because the continents separated them. It's very sad. As said previously, certain geology exists on both sides of the Atlantic Ocean. Why is that? Why do the mountain ranges on the eastern side of North America and the western side of Africa and Europe all bear striking similarities? Maybe because they once were originally the same mountain strain. And more so later on than we had, but paleoclimate evidence. We have coal all around the same locations. Why? Because maybe they were once all touching each other. It's not separate, isolated deposits of coal covering the world. It was one coal bed that was broken up. And the same argument was made from glacial ice. So Wegener had all these points. He was like, hey, this seems to look like a continent exploded and was sent in all directions. Cool. That seems reasonable. How did that happen? People would ask him. Ooh, that's a tough one, right? I don't know how continents move. Continents are big. Maybe he thought gravitational forces, the moon, the sun. Uh, Maybe the continents drove through the ocean somehow. These were issues he had. He didn't have a good example, so the scientific community didn't necessarily believe his argument because you don't just need to have evidence; you need to have a way for it to work. Wagner didn't have that, and he had actually died before his theory was commonly accepted on a Arctic rescue expedition. Back in the day, scientists went to Antarctica and the Arctic all the time. They were pretty cool like that. World War II rolls around, Great Lakes foreign technology, a lot of people cross the Atlantic, and we notice something interesting. Namely, aside from that parallel shoreline that we talked about before, there seemed to be some sort of ridge system that extended through the ocean. Shown here is the Mid-Atlantic Ridge System. This ridge system is the result of the asthenosphere. It was the result of the asthenosphere pushing that rigid crust, separating it out, right? Rigid crust on top of semi-plastic Greek layer. Strong rock can flow over semi-plastic layer, as I said previously. I will, before I go any further into this conversation, a lot of these slides do loop back on themselves. I will be repeating myself because these are points that are important to be made. So just wanted to get that out there before we continue. So we noticed that there was this layer, this line running through the Atlantic, and as we took our boats over it, as we did studies on the ocean, we noticed this weird sediment thickness going on with the Atlantic Ocean. In so much that at the center of the Atlantic Ocean, on that Mid-Atlantic ridge that we talked about, sediments are very thin. And as you expand out further along towards the continents, the sediment started getting thicker. Why is sediment very thin at the center and very thick at the end? If the Atlantic Ocean has always been here like the Atlantic Ocean, wouldn't you expect sediments to be uniform throughout? Interesting. And as we talked about from chapter 1, the things on the bottom, things that are lower, we think of as older. Things in the top, we think of as younger. Interesting. So you have thicker sediment, older sediment closer to the coastlines, younger sediment on the inside. Interesting. So before we go into really the final swing that showed plate tectonics to be a factual and accurate representation, let's talk about the magnetic field of the Earth. I'm sure you're aware the Earth has a magnetic field, right? I'm sure, seen a compass at some point in your life. And the magnetic field of the Earth works, essentially, we can consider it working like a dipole magnet. A dipole magnet is a ball magnet like shown in this picture. Within the interior of the Earth, this magnetic dipole-esque field is formed and radiates out throughout the Earth. Sometimes igneous material that has something that is magnetic, like iron, will cool and will capture the polarity of the Earth at that time. Essentially, you could consider iron having little magnets in it, and then when the rock that holds the iron solidifies, the magnets stay pointing in that direction. So if you have a change in the magnetic field, igneous material will cool in that change in magnetic field, and the compass needles in the rocks will point in a different direction. This is something that happens lots throughout the history of the world. This magnetic field has shifted many times, and we know this because we can look at a layer of rocks and we can see these magnets in the rocks flipping back and forth. And the magnets in these rocks that are of this certain age point this way, and I can go to the other side of the world, I can find those same rocks of that same age pointing the same direction, meaning this is a global event, right? So that's the quick and dirty, again, real deep subject, but that's magnetic fields. So what we noticed when we drove across the Atlantic Ocean was that the magnetic field seemed to stripe, if you will, along the Atlantic Ocean, such that at the very center of the Atlantic Ocean, on that ridge axis, there was a certain polarity, a certain direction of the magnetism. And then if you go equidistant, equal distance from the ridge, from that center ridge point towards Europe or towards America, at the same distance, you'd have a flip of the magnetic field. The magnetic field would point from north to pointing south. And it would keep this north-south orientation flipping equal on both sides as you cross the Atlantic Ocean. So much so that the same distance, if you're like halfway between the ridge and Europe, you have the same magnetic field in the rocks as you have halfway between North America and Europe. And the coastlines of Europe and North America have the same polarity. What does this mean? Well, if we connect this with the other things shown earlier, namely the sediment thickness, the fossil and geologic evidence, the way things seem to just piece together well, what we find is that this is evidence, this is a mechanism showing the Atlantic Ocean essentially pushed Europe and America apart, and Africa and South America pushed it apart. And it pushed it apart by creating new ocean floor. We have young ocean floor at the mid-Atlantic ridge, and the ocean floor gets older as it actively pushes out. Africa and South America are being shoved away from each other by the Atlantic Ocean. This was the final swing that really solidified this as a true statement. And we found this same interesting development throughout the world. Again, we can see picture B here. This is in the Pacific. We have these same things occurring. Cool. Ooh, my internet connection is unstable. I hope things keep going for you guys. So, two independent groups of geologists published seafloor spreading hypothesis in the 60s, including this evidence that we just talked about. Said new ocean floor was created at mid-Atlantic ridges, and old ocean floor destroyed the deep ocean trenches, leading to eventually the theory of plate tectonics. Cool. Wegener was correct. Wegener didn't know why he was correct, but Wegener was correct. Good for him. So, now we can talk about theory of plate tectonics again with an asthenosphere that exists below the lithosphere. Again, lithosphere is the crust, asthenosphere is the mantle, for sake of conversation. And the crust floats on top of that asthenosphere. And whatever the asthenosphere is doing, the crust or the lithosphere rides along with it. So if the asthenosphere underneath the Atlantic Ocean is flowing in such a way that it wants to push America, the crust, the lithosphere, the crust as America, towards the west, it'll do that because the lithosphere is floating on top. I hope that made sense, right? This is a lot deeper subject that I can cover in, a quarter of a chapter. But I hope the understanding at least is there. Cool. So we now know what's going on with, for example, the Atlantic Ocean. We can define it. We define this separating, this pushing at the mid-Atlantic ridge system as a divergent plate boundary. Divergent, diverge, push, right? These are constructive margins, meaning they construct something, they create new lithosphere, they create new crust. This happens when two plates move apart, the mantle material upwells to create new seafloor, and these plate boundaries, for example, located at ocean ridges. As you can see from this diagram here, you have the asthenosphere melting, coming up. The new crust you have essentially is the solidified asthenosphere that was once the plasticky mantle. This process explains the age of ocean floors, how we have younger sediment in the center, older sediment at the edges, and the magnetic stripping that we saw. The magnetic stripping, as said before, involved normal and reverse polarity, switching the magnetic field over time, and is actually evidenced on land as well, funny enough. The Mid-Atlantic Ocean the mid-Atlantic ridge system goes through the middle of the Atlantic. Iceland happens to sit on top of that ridge system, so we can go to Iceland and we can see this rift system on land, as shown here. Pretty cool stuff, right? Iceland's being like ripped apart by the mantle. Divergent plate boundaries also exist within continents, as shown here. Same process applies. This essentially was the top of this list was the Atlantic Ocean before it was an ocean. This process here shown is more or less what the Atlantic Ocean went through. As the Horn of Africa is actively undergoing this right now. You can go there and you can watch essentially an ocean being formed on the eastern part of Africa. Pretty cool. So we had divergent plate boundaries where they separated. Convergent plate boundaries is where they come together. These are called destructive margins because the plates collide with each other. Ocean trenches are formed and the ocean lithosphere is subducted into the mantle. So let's go over a couple examples of this. And this will make a lot more sense when you see the pictures of what goes on. So we have, as I said before, we have different types of crust, right? We have oceanic and continental crust. Oceanic crust is the ocean, continental crust is the continent. When you have an ocean crust connecting with a continental crust, the denser ocean slabs sink into the asthenosphere. Why are they more dense? Oh, because they have all that water and stuff, right? There's more density in water than there is in air. The pockets of the magma develop and rise, creating volcanoes and creating mountain chains such as the Andes, Cascades, and Sierra Nevada systems. This picture does a lot better job explaining what's going on than me talking about it. You can look at this and you can see South America. It's the west side of South America. Large trench system, volcanoes and mountains being formed. What happens here is the ocean is pushing from the left to the right. The ocean is pushing into the continent, but since the ocean is lighter, it's going to be shoved underneath. As that ocean is shoved underneath, as the ocean rock, the ocean crust is shoved underneath, eventually it goes deeper, deeper, starts getting hotter, hotter, melting, up pops volcanoes. Wherever we find ocean connecting with continent in this way, we see these volcanoes and these mountains forming in this exact measure. And that trench is actually where the two crusts, where the two plates connect. Here they have an example from North America with Mount Adams, Mount Rainier, Mount Hood, Mount St. Helens, very famous volcano, right? And that's exactly what's happening in this location. That was an ocean continent. Now we can also talk ocean-ocean. Ocean-ocean occurs when, well, again, two oceanic slabs converge and one descends beneath the other. These form volcanoes in the ocean floor and volcano islands, such as the Aleutian Islands in Alaska. Why does one ocean fall below the other ocean? Well, you'd have to ask those individual plates why one went one way and one went the other way. Usually has to do with density and things like that. So notice here the trench occurs on not on a connection with the continent, but on a connection with another ocean plate. But you still have the same repercussions. You still have the mountains being formed and the volcanoes being formed because the ocean's being subducted. I said the Aleutian Island chains in Alaska are an example of this. Two oceanic plates connect, one sinks below the other, giving yourself volcanic islands. No new ocean floor is created at divergent plate boundaries, and subduction of ocean floor destroys ocean floor. Doesn't really destroy as much as it recycles it to create something else. Continental crust and the lithosphere are less dense than the ocean sphere, so they don't subduct, right? The deeper thing is what's poured underneath. The oldest continental crust we have is about 4.1 billion years old, mainly because it doesn't get subducted as frequently. If you find a location, such as the Canadian Shield or certain parts of Australia, where nothing's really tried to take down the crust isn't taken down. So the third, I'm sure you could have guessed this, is the continent-continent convergence, where two continents collide. In this case, it's not an obviously less dense, not an obviously more dense material, such as ocean. So the less dense continental material does not subduct. This produces high elevation mountain ranges, such as the Himalayas. I say the Himalayas because the most common, the best used example of a continent-continent collision is India. India drove north really fast some 70 million years ago and smashed into Asia. And when India smashed into Asia, it shot the Himalayan mountains up. As we can see this example here, India's coming in, closing the gap between the ocean. That ocean there is essentially being crushed in underneath, as we can see at the back here. So the Indian subcontinent is shoving that ocean basin between them and Eurasia down below Eurasia. And eventually, India collides with Eurasia. Eurasia's larger. Eurasia wins the fight. India goes shoved underneath. But since they're both similar densities, it doesn't go quite as well, and you have a lot larger buckling effect. Right? Essentially, this would be take a piece of paper, push your hands together on top of the paper. What happens? The paper bulges up, right? That's what the Himalaya mountains are. That's why they exist in the place they exist. Here's a picture of them. Cool. I get the feeling you may have seen a picture of the Himalayas before. So we talked about all these plates colliding, subducting, breaking apart. What if those things? What if the plates don't do that? What if the plates don't necessarily interact with each other, but next to each other? If you have plates that slide by one another but don't run into each other, you have what's known as a transform plate boundary. No lithospheres created or destroyed at these, and this is essentially plates moving past each other. An example being the San Andreas Fault. So what happens with a transform plate boundary is, as I said before, the lithosphere is what guides, what directs the crust, right? Since the lithosphere is guiding, directing the crust, it doesn't have some sort of overarching plan, right? It's not trying to do something. It's responding to the heat being released by the inner core. We talked about that in chapter 1. So sometimes plates will move more or less parallel with each other. In this case, the Pacific plate is moving towards the northeast. The North American plate is moving towards the southwest. They're sliding along each other. That the point where they are sliding is the San Andreas Fault system. Notice above the San Andreas Fault, we have a subduction zone, the Cascadias, creating, again, right, that mountain chain up there. But that is because the Juan de Fuca plate is landing in there. Not necessarily because the Pacific plate is doing that, just that smaller subplate. And cool story, again, as I said before, geology is very much an observational science. You can go to the San Andreas Fault and look at it. You can see the San Andreas Fault do what it does. Pretty cool, right? The fault, that creek there, as shown here, I think it's dry in the picture, but in the geologist sketch, it's more obvious. That creek didn't always have that long path there along the fault. The creek was once straight. The fault stretched the creek out along with its transformation. Continuing this trend, right? Transform boundaries. Essentially, we separate them into 3 distinct categories, but in reality, they all interplay and work with each other. A divergent plate boundary will have transform action going on inside of it, and maybe some convergence as well. Mid-Atlantic Ridge is full of lots and lots of fracture zones, sprain zones, and transform faults. And you can see all those lines slashing across it between South America and Africa. All this, as we said before, showed Wegener to be correct. We still call it Pangea the way he did. And now we can very accurately demonstrate the movement of the continents and the movement of the plates. They were all together some 200 million years ago in the late Jurassic. So we have fossils from the Jurassic period connecting all these parts. As these continents moved away from each other, we can see India cruising up to smash into Eurasia. North America and South America grow, change. Everything happens the way it happens. We have evidence for this existing the way it exists, and it's pretty fascinating. Also, I will notice before we continue, notice that not all the continents are in the same location that they are now. For example, Antarctica up pretty high, right? Antarctica was 200 million years ago around where South America is. It's not South America, around where South Africa is now. So that's why we can have corn and jungles and fossils of non-Arctic animals in Antarctica, because Antarctica once was not in its current location. Present day motions have extrapolated in the future 500 million years, 50 million years from now. So essentially, what's the world going to look like in the next big geologic time jump? Something like this. Notice the Mediterranean and the Red Sea have closed off. India's still punching in there. North and South America have spread further away from Eurasia and Africa. The Atlantic Ocean is a lot larger. And these trends more so are following current motions in the asthenosphere and the lithosphere. If things decide to change, things will change. Cool. Talked a lot about plate motion and plate contacts. Let's talk about stuff with inside plates. For example, hot spots and hot tracks, such as Hawaii. Hot spots or mantle plumes are caused by rising plumes of mantle material and heat. Volcanoes form over them, such as the Hawaiian Islands, and these produce very long-lived structures that originate at great depth, perhaps the mantle-core boundary. What happens in a hot spot, again, such as Hawaii, is within a plate itself, you can have bits of mantle coming up, say through some crack or however it wants to choose to come up, and producing mountains in the same way they produce at convergent zones. However, since we're kind of in the center of a plate, you don't have two plates causing this, you just have drops up, and that plate is moving over that mantle plume location. You can have what's shown here. Hawaii, the largest island of Hawaii, is the youngest. And then Maui, Molokai, Oahu, and I'm terrible with Hawaiian words, sorry, all are different ages because they show the path of the plate over this hotspot. So the plate that the Hawaiian Islands sit on has been rotating and moving over a plume location for the past almost 6 million years. And in a few years from now, if this mantle plume location keeps spinning up mantle, we're going to have more Hawaiian Islands. Cool. Talked a lot about movement of this, magnetic that, paleomagnetism. Paleomagnetism is essentially the study of all the things we've been talking about. The study of magnetism, of rocks, going back throughout the history of the Earth. What paleomagnetism allows us to do is not only say what the magnetic field looked like north-south in a particular location, but also what the magnetic field was acting like at any given moment. There's such a thing called the apparent polar wander path. What that stands for is the North Pole of the Earth is not always at a particular, the North Magnetic Pole, sorry, is not always at any particular location. Over time, and by a particular location, I mean more so modern Antarctica. Over time, that North Pole has ebbed and flowed and wandered around, giving very distinct and unique magnetic fields on the Earth. So we can study the magnetic fields captured in igneous rocks over millions and billions of years, and we can recreate, in essence, what the magnetic field looked like millions and billions of years ago, and use that information to understand the way the continents moved and the way mountains formed, oceans formed, things of that nature. How do we measure this plate motion? Well, we can use hotspots, as said before, or since we live in the future, we can use GPS. We can find a point on a continent and say, you are here, come back after an amount of time and see if that position is the exact same location. That's pretty cool, right? Geologic evidence of plate motion. Knowing the ages of the seafloors, we can tell how fast plates are moving, how fast continents are moving. They don't move too fast, right? But they can have some hoof to them if they really want. Here is a diagram showing relative plate motions to each other and direction. As of it appears to be, I don't know when this map was created, but it's more or less probably still accurate. And what this tells us, for example, is, as said before, Eurasia and North America moving apart from each other, right? The Atlantic Ocean is spreading right there. Pacific plate moving very fast. If you ever heard the Ring of Fire, lots of volcanoes and stuff going on around the Pacific Ocean, that's because the Pacific plate is moving and lots of mantle is coming up and traveling around. And we're talking, what, 10 centimeters per year? Doesn't seem like that big of a jump, but if you're talking a continent moving 10 centimeters per year, that's something that's noticeable. After 10 years, you have a meter of movement. Something that 10 years ago was here is now a meter to the left in the grand scale of things. And that's something that GPS verifies, which is oh so cool. At least to me, because, I love geology. So, what are the driving mechanisms of plate tectonics? Well, no one model truly explains plate tectonics in its entirety. Because we're talking about the center of the Earth, I can't necessarily go into the Earth and look at it, right? It's generally agreed upon that Earth's heat is the driving force behind this motion and behind what causes the asthenosphere, to convect around. Models proposed, such as slab pull and slab push models. Why is a continent moving? Because it's being subducted, it's being dragged down, so the entire continental plate will move to follow it, as shown here. So you have this continent in the center. So you have that trench to the left and the ridge to the right. The crust between the trench and the ridge is being pulled to the left. It's being pulled down by the continent ocean margin there, and it's being pushed by the mid-Atlantic ridge system. So if you, for example, had an island in between that trench and that ocean, that island is being dragged towards the continent and being pushed towards the continent at the same time. Does that make sense? I hope it does. Plate mantle convection is another perceived method for this. This is the layer cake model, essentially, the whole mantle convection model. And essentially what goes on with the whole mantle convection theory is similar to boiling a pot of water, right? You get yourself a pot of water and you put, say you're doing macaroni or something like that. You get it boiling. Eventually that water is going to start rolling, right, as it boils. As it starts rolling, the macaroni is going to move around within the ocean. If you have a piece of macaroni floating on top, it's going to move around with the convection of the water. The argument is that since the asthenosphere is plasticky, has some motion to it, the asthenosphere would have these same convection currents because of the same reason the pot of water. The core of the Earth is super hot, letting out heat. It's rising. That heat is rising through the mantle, causing it to move. And the lithosphere essentially is floating on top of the mantle. So if there's a convection current within the asthenosphere, within the mantle, the crust is going to float along top it. In reality, it's probably this and the other thing working together to cause things to move. But it's a pretty cool concept, right? To think that directly below your feet is thousands of kilometers of impossibly hot plastic that you're just surfing along. It's kind of a cool thing to think about. XKCD did a really good comic on that. I think I've said that already. Layer cake model. not really as common. I think most people prefer whole mantle convection, but essentially instead of the whole mantle floating around, just the top flows around. Uh, cool. That is chapter 2. As I said before, I don't go over these questions necessarily in this conversation. However, I will scan through them just so you can look at them yourself. Are there any questions about anything that we've covered so far? If you got, raise your hand. Oh, hey.
I'm just looking at the chapter 2 questions that you sent through email.
Yes.
And number 3 about the shield volcanoes on Mars.
Yes.
I guess the only thing that I can think that would affect that is gravity and not so much plate tectonics. I guess could you explain that a little bit, how that would work?
Sure. So we didn't really cover volcanoes too much, right? But we did do a little bit about them. What a shield volcano is essentially a volcano that doesn't have a lot of motion going on with it. A volcano that can continue to grow and grow and grow and grow. When the volcano lets out magma, the magma just kind of sits on top of there and continues to grow. So when you have, I'm trying to find a picture of volcano someplace. So when you have, and the idea that question is supposed to ask is, in Mars, we don't have any plate tectonics. So you don't have anything to destroy the mountain, destroy the shield, given time. A modern volcano, for example, Mount St. Helens, over time, something's going to recycle that volcano away. Something's going to chew it up and spit it out and create something else. Because all the rock on the Earth is constantly rotating around. Hawaii, where's the picture of Hawaii? Hawaii is some of the islands of Hawaii are smaller than others. That may be in part because those islands are kind of being beat up more. There's lots of, there's erosion and stuff like that too. But what that question's trying to get you to understand is that all that rock is being recycled. And on Mars, we don't have active tectonic. That rock just sits there and winds or anything that does anything to it. And therefore, it can grow larger and larger and larger because it's not being actively recycled. Does that work? Does that make sense?
Yeah, that makes sense. And then for number 4, did you want us to include one example picture of each type of boundary or just pick one?
If you can do all 3, that'd probably be preferred, yes.
Okay. And then could we just email you the answers, or I don't know how you wanted us to.
Yeah. I stopped recording. I don't think this is